All right, I thought I'd go through an example when the first step is fast and the later step is slow. So as I mentioned in part 3, things are more involved if this happens. Remember, you're not allowed to include an intermediate in a rate law expression. So let's consider this reaction that someone did in the lab. They mixed NO with Br2, and this is the stoichiometry here. They did some experiments and they showed that it was second order in NO. Whoops, looks like I got a little mistake there. A second order in NO and first order in Br2. So I actually had two mistakes in here. All right, so here's the proposed mechanism that the chemists did. They said the first step was fast and the second step was slow. Is this mechanism consistent with the observations above? Remember, a mechanism has to qualify in two ways. It has to add up to the overall reaction, and it has to conform to the observed rate law. So let's see if it does that. First, does it add up to the overall reaction? Yes. If you add up these two steps and cancel something that appears on both sides, you get 2NO plus Br2 gives 2NOBr. Notice that there was an intermediate, and that's going to become important. We have to derive the rate law from this. So the rate law of the reaction is the rate law of the slow step. So that's the second, that's rate constant K2 times NOBr2 plus times NO. Remember that the rate law of a rate determining step exactly matches the molecularity of that reaction. So this is first order in NOBr2 and first order in NO. Okay? We cannot report this as the rate law, though, because it contains an intermediate. We have to make a substitution. This is where you use the first step, which is set up as an equilibrium. And notice what I did here. I wrote that the rate law for the forward reaction, K1NOBr2, is equal to the rate law for the reverse reaction, K minus 1 times NOBr. The rate of the forward is equal to the rate of reverse. That's what's equal in an equilibrium. It's not amounts of things, it's the rate. Now you have to rearrange this and isolate the intermediate. So the intermediate is NO. I keep making mistakes. I'm really sorry about that. It's NOBr2. And so I want to rearrange it to isolate the intermediate, NOBr2. So I put the K minus 1 in the denominator on the left, and you can see that this expression is equal to the intermediate. So that expression that I just circled gets plugged into the proposed rate law there. And what do you get? Well, notice that you get a bunch of K's, NO squared, because one of them came from our substitution and one was already there, then times Br2. Now, usually chemists don't write the individual K's. They'll just write K observed. Or I noticed that your textbook uses K prime. You could use either or. It's also important to remember that all of these K's I mentioned are lowercase k's. The only time you use a capital K is what I did on the previous slideshow when the capital K represents an equilibrium constant. And so you could refer back to that. So notice that this is the same rate law that I had on the previous slide. So let's try an exercise that you can do. So you do this one. You could stop the tape and then try it and then compare it to the answer on the next page. So this is what I did. I took the mechanism, I got rid of the intermediate, and I added it up. And this is the overall reaction. Then I took the rate law of the rate determining step, which is the second step, the slow step. And so that's going to be K2, the rate constant for that step, times HI to the first times ICL to the first. But, as we said, intermediates are not allowed to be in rate laws. So I'm going to use the first step, which is fast, to make a substitution. So the rate law of the forward is K1 ICL times H2 is equal to the rate law of the reverse, K minus 1 HI HCl. Now I'm going to isolate the intermediate, HI, and I get this expression. It looks a little ugly, but just make sure you write it correctly. unlike your dad on the previous one. So that big box gets plugged into the rate law that we did above, and we get this expression. As I said before, usually people don't report the individual little k's. They'll just write one k like I did here, k observed. Now this one's probably different from something you've seen before. It's second order in ICL, first order in H2, and negative first order in HCl. HCl, remember, is one of the chemical products. What this is actually saying is the rate slows down as you build up more product. The rate constant stays the same, but the rate slows down. I hope this helped. Don't hesitate to ask any questions. You can call me all day today or tomorrow, and I'm happy to help.